Hello everyone, thank you for joining my presentation. I'm Kento Nozawa. I'm going to present PAC-Bayesian contrastive unsupervised representation learning. This is a joint work with Pascal Jamy and Benjamin Gage. In this work, we analyze contrastive unsupervised representation learning, shortly CAR. CAR is a popular class of representation learning algorithms last few years. CAR aims to learn a feature extractor F, such as neural networks that extract a good feature vector by solving a contrastive unsupervised task. Roughly speaking, CAR assumes that we can access triplet of samples, a base sample X, for example a cat image, and similar sample X plus, for example another cat image, and dissimilar sample X minus, for example fish and chips image. By minimizing the contrastive loss, small l, feature extractor F maps X and X plus to similar representations, and X and X minus to dissimilar representations. In this context, similarities depends on the definition of the contrastive loss L. In our paper, higher inner product means more similar. Learned feature representations are used for downstream tasks such as classifications or regression. In the downstream task, learned F is fixed, and we only train a classifier G such as linear classifier or another neural network. In practice, this supervised performance is really well even if we use linear classifier. But there are some questions about CARs. Why does CAR give a good feature extractor for supervised tasks? And can we get some theoretical guarantees such as PAC bound? The previous work by Aurora et al. Showed the first PAC bound for CAR. They showed that contrastive unsupervised loss plus Rademacher complexity-based complexity term O is an upper bound of a kind of supervised loss. So the main message of the bound is that finding a good representation F hat by minimizing contrastive loss can guarantee to generalize well on the supervised task. In this work, we extend their approach for theoretical understanding of CAR. We show the first PAC-based bound for CAR and derive the algorithms by minimizing the bounds. Technically, we replace Rademacher term in the previous Aurora et al.'s bound with Kalbach-Leiber divergence, which is easier to compute in general. Therefore, the PAC-based bound suggests a theory-driven learning algorithm. We also show another PAC-based bound for non-IID data assumption. The existing bound and our first PAC-based bound require IID assumption for contrastive data. But IID assumption is often violated for practical contrastive dataset. For example, similar sample is generated by using data augmentation of base image X. I briefly introduced the general PAC-based bound. PAC-Bayes is a Bayesian flavor PAC learning framework. It uses a posterior Q that is a probability distribution over a function class F, for example neural networks. Q can be optimized by using training data. The PAC-Bayes also require a prior P over the same function class, but K cannot be optimized by using training data. Then, by using posterior Q, test risk is defined as expected loss Q on the test data distribution, and R hat is an empirical counterpart. Then PAC-based bounds show a generalization error bound for posterior Q with high probability 1 minus delta. The key message of the bound is that test risk is bounded by empirical risk plus complexity term that contains KL divergence between Q and P. We show our first contribution, a PAC-based Karl's bound. Here is a high-level bound. The key message is the same to the previous Aurora et al.'s bound. However, since all terms in the right-hand side are explicit or easy to approximate, so we can evaluate generalization error bound and minimize the bound directly. I give high-level information of our Karl algorithm. From the previous upper bound, we minimize the right-hand side of the inequality in empirical unsupervised loss L hat and complexity term with respect to the posterior Q. We assume P and Q are merge-biased Gaussian with diagonal covariance. That means feature extractor X weight are sampled from Gaussian. So we optimize Q's mean and covariance by using SGT by following Dugard and Loy's method. At each iteration, we approximate L hat by sampling weight of the neural network from Q. And thanks to the Gaussians, KL divergence has closed form. In our experiment, we train Q on contrastive unsupervised data. Then we compare the test 0-1 risk on supervised data by using centroid classifier. We conduct numerical experiments to verify our proposed algorithms compared to supervised and existing contrastive methods. The bold numbers in the table show the lowest value amongst contrastive algorithms per evaluation metric. So the proposed algorithms give a good feature such that the classifier can achieve competitively lowest risks. In addition, our algorithms also give non-vacuous generalization error bound. Our paper contains more empirical results. I summarize this talk. We provide the first PAC-Bayesian generalization error bound for Karl. This analysis allows us to derive new algorithms by directly minimizing the bound. In our paper, we also show more general PAC-Bayesian bound for multiple dissimilar samples. In addition, we also show PAC-based bound and its minimization algorithm for non-IID setting. Thank you for watching.